Hello, my name is Xi Liang. I'm a PhD student at U Chicago. Thanks for joining my presentation on our paper Combining Aggregation and Sampling Nearly Optimally for Approximate Query Processing. When we use sampling for approximate query processing, the quality of the answer solely relies on the quality of the sample. As shown in this toy example, we have a collection of balls of different values in 3 colors. With random sampling, we might end up with a sample that contains no green balls because it is the smallest group. Uniform sampling is easy to implement, widely applicable, and it can handle high-dimensional queries. But as shown in this example, it might miss outliers and fails on highly selective predicates. Stratified sampling is designed to preserve every group from the population, no matter how rare it is. For example, here we first stratify the balls by their color, then we draw samples from each color group. However, even though we can now preserve rare groups, we might still miss the numerical outliers, which could introduce large error for aggregates like sum. When we apply stratified sampling to AQP, given a storage constraint, we need to decide which columns to stratify on and how to stratify, and it can be formalized as an optimization problem. Instead of sampling, we can also use pre-computed aggregates. For example, we can calculate the mean, max, count, and sum of each stratum and use them for estimation. Aggregates are like materialized views. When a query aligns perfectly, we can have accurate answer. Otherwise, we can derive an upper bound and a lower bound. Problem with using stratified aggregates is that the error is fixed if predicate does not align with the strata, and the storage cost increases exponentially with the number of dimensions. Previous work have tried to combine aggregation and sampling for better performance, but this direction is still relatively less explored. For example, AQP++ construct a prefix cube and optimize the construction of the cube by using a greedy hill climbing algorithm to determine aggregate computation, and then it combined the cube with uniform sampling. Revisiting reuse caches previous query results to augment samples. It is designed for a conversational data exploring process, which assumes previous queries are highly correlated with future ones, and there are some idle time between queries that can be leveraged by the system. In this paper, we propose PASS, a novel approach to combine stratified sampling and aggregates. The first component of PASS is a partition tree. Each node of the tree contains one or more predicates and a summary of the tuples that satisfy the predicates. The leaf layer of the tree forms an optimal partitioning of the dataset. The second component of PASS is a collection of stratified samples, and each stratum corresponds to a leaf node. For each stratum, we sample from the tuples that satisfy the predicates of a leaf node, and we store the sample for later use. This design has several benefits. First, the hierarchical structure of the tree makes it possible for us to store the traversing early when serving a query. Second, accurate summary gives an accurate answer if query aligns perfectly with the predicate. Third, our partitioning algorithm applied to the leaf layer minimizes the max error. And lastly, the strata mapping in the leaf layer enables sample skipping when solving a query. Now let's look at a concrete example. Suppose we have a dataset of 2 columns, A and B. We want to solve queries that aggregate on the B column with predicates on A. We could construct a path synopsis like this. We have the partition tree. Each node contains one or more predicates and the summary of tuples that satisfy the predicates. We also have the optimized leaf layer and strata mapping to the leaf nodes. More specifically, in order to have the nice properties we just mentioned, the partition tree complies with the following invariants. First, each layer is a partition of the entire dataset. Second, the children form a partition of their parent node. Third, the siblings are disjoint. We design paths to handle aggregate queries of this form. We focus on rectangular queries, and our technique can be easily extended to support group by queries by considering the group by conditions as an additional predicate, then combine the results. The scope of our technique is similar to previous work that are designed to support a query column set like BlinkDB. To solve a query with paths, we first decompose the query into two parts. Rcover are the partitions that are fully covered by the query, and Rpartial are the partitions that are intersecting but not covered by the query. We then solve the subquery related to Rcover using aggregates. This step will give us an accurate answer A for the subquery. Then we solve the subquery related to Rpartial using sample. This step gave us an estimation S and a confidence interval Ci. Our final answer is a combination of A and S with error estimation Ci. Now let's talk about our partitioning algorithm for the leaf layer in 1D. Suppose we want to partition the dataset into k buckets over attribute C1. Let n be the cardinality of C1. There are n choose k ways to partition the dataset. On the other hand, at most we have O n square queries with different predicates on C1. The objective of our partitioning algorithm is to find the partition that minimizes the maximum error of a query template. And as we discussed earlier, errors are only introduced by the partially intersecting partitions. Intuitively, our algorithm is similar to the one from the optimal histogram, and it can be solved nearly optimally with dynamic programming. Unlike the V-optimal histogram that only deal with one attribute, our algorithm partitions on the predicate attribute to optimize for the aggregate attribute. Naively, our DP algorithm runs in OKN24, and it is optimal for average query and root to approximation for sum and count queries. Because the naive DP algorithm is too expensive, we also proposed a couple practical extensions. For example, we can optimize the DP algorithm by applying monotonicity and binary search. We can also use a sample instead of the entire dataset. Lastly, when estimating the error of an interval, we could use a subset of interval instead of enumerating all of them. Details can be found in our extended paper. With the optimal partition, we can build the leaf layer and calculate the summaries. During the process, we can also construct the sample for each leaf node. Once we have the leaf layer, we can construct the partition tree bottom up by merging two neighboring nodes until we reach the root. To handle high dimension, we use k-D tree. We start with an empty tree. While the number of leaves is smaller than k, we will find the leaf node V with the maximum error, and then we create the children of V. The k-D tree we constructed this way is an optimal k-D tree for average queries and a root of k approximation for sum and count. In our experiment, we use 3 real-life datasets. We compare paths with 5 baselines, including 2 sampling baselines and 3 recent AQP techniques. The first one is VerdictDB. During pre-computation, VerdictDB constructs a synopsis called Scramble, which is a collection of samples, and it further optimizes the samples as it processes more queries. DeepDB is a machine learning technique that learns from the dataset itself. AQP++ combines a prefix cube with uniform sampling, and it uses greedy algorithm for aggregation construction. We use 3 variations of paths to better understand how sample skipping affects the performance of paths. Due to our unique design, paths can skip sampling from irrelevant partitions and partitions that are fully covered by the query we want to solve. Given a sample rate gamma and the data size n, we define effective sample size, ESS, to be the number of samples that are used to solve a query. And the budget we are allowed to use is given by gamma n, which equals to the ESS of uniform, stratify, and AQP++, because they do not skip samples. For PAS, when sampling from certain partitions are skipped, our population size is less than n. Therefore, the ESS PAS is less than the budget. Because samples are the main source of overheads, dealing with less sample leads to a lower latency. This also enables us another option, which is to use more sample from partitions that we do not skip to further improve accuracy. As long as the total number of samples we actually use is less than the budget, there's no additional overhead. The first PAS variation is called PAS BSS NX. BSS stands for bounded sampling size. With this variation, we want to use more sample from R partial to improve accuracy. To achieve that, for BSS NX, we store a sample of size n times budget in the strata, just to make sure we have additional sample available for R partial. But it is still possible that the budget is not fully utilized if n is not big enough. To demonstrate the best case scenario, we build PAS ESS. In PAS ESS, we make sure we can fully use the budget. In the first experiment, we compare PAS with uniform sampling, stratified sampling, and AQP++. We randomly generate workloads of 2000 random 1D count sum average query for the 3 datasets. We measure the median relative error and the average pre-computation cost. From the result, we notice that PAS requires a higher pre-computation cost, but it is more accurate than the baseline. In this experiment, we compare PAS with VerdictDB and DeepDB. We use a full-size VerdictDB, i.e. VerdictDB 100% and VerdictDB 10% that use only 10% of the storage of the full-sized version. Similarly, we train a DeepDB 100% using the entire dataset and DeepDB 10% with a 10% sample. We randomly generate 2000 1D sum query for each dataset and multiple dimension queries for the NYC dataset. We measure the median relative error, average pre-computation cost, latency, and storage. In this table, we first notice that even though the latency of VerdictDB 100% is only 1/3 of MySQL, it is still much higher than the other baselines. And the latency of PAS is comparable with VerdictDB 10% and DeepDB, but it is much less than VerdictDB 100%. This is also because VerdictDB 100% maintains much more samples, as we can see from the storage cost column. We notice that PAS use much less storage than other baselines. The pre-computation cost of PAS is also comparable to other baselines. On the accuracy side, we notice that VerdictDB 100% has the best accuracy in terms of relative error that is less than 0.5%. But VerdictDB 10% has the highest error, which is more than 90%. We also notice that DeepDB's accuracy drops drastically on Instacart dataset and have a much higher error on the higher dimensional queries. For PAS and VerdictDB, as we increase the storage size, we notice an improvement of accuracy because there is more sample available. But this is not the case for DeepDB. Overall, we can see that PAS is competitively accurate with the best baseline while keeping the cost at a favorable level. Here's why we think PAS outperforms the baselines. Comparing with AQP++, PAS use the optimal partitioning algorithm at the cost of a higher pre-computation cost. Also, being able to skip samples make it possible for PAS to use its budget on the partitions that can reduce errors. PAS is not directly comparable with VerdictDB and DeepDB because unlike VerdictDB and DeepDB that are designed to handle ad hoc queries, PAS is designed and optimized for query template. We think that's one of the reasons why the end-to-end performance of PAS is better than the other two when the cost is similar. As a conclusion, in this paper we propose PAS, a novel synopsis that combines sampling and aggregates nearly optimally And we show in our experiments that path is efficient, lightweight, and accurate. In our future work, we plan to tackle the challenges we identified when use path to solve multidimensional queries. We also plan to improve path to handle insertions and deletions of the data. With that, I'm happy to take any questions. Thank you.